Chemical kinetics is a really interesting part of science. It's actually more than just chemistry. It's actually science itself. And if you look in the lower right-hand corner, there's kind of a scale. And one side says kinetics and the other side says thermodynamics. And we'll talk about that here. Thermodynamics, which is enthalpy, delta H, and all that kind of stuff. Enthalpy is very useful to tell if a reaction is product or reactant favored. And more often than not, exothermic reactions are product favored. So if you wanted to know if any given reaction was going to happen, more often than not, if you study the thermodynamics and specifically enthalpy, you can tell if the reaction is exothermic, then it's probably going to happen. On the other hand, if it's endothermic, it won't usually happen. We'll talk more about that in Chem 223, what makes up these thermodynamic arguments. However, just because a reaction is going to happen, it doesn't say anything about how fast or how slow the reaction takes. And that's an interesting thing because we as human beings with, say, 70 years, whatever, on average life, all right, and also being impatient, if you're like me anyway and stuff, we tend to need things that are in our time frame in the world of humans, all right? We don't want to have to wait, say, 10,000 years for reactants to go to products. Thermodynamics is great about telling if a reaction is going to go or not, but it doesn't say how fast or how slow. And this is a real difference now. Thermodynamics doesn't have any information on time. So kinetics is the study of reaction rates, all right? And a reaction rate is basically a study of the time. And the study of the rates cannot happen unless you think about how the reactants go to the products. And this is called the mechanism. And the mechanism helps us understand why the reaction rates are as they are. And both these things together, reaction rates and mechanism, will help us to understand how long the reaction goes. So again, you have a reaction, it's supposed to go according to thermodynamics, cool, all right, but does it take 1 year or does it take 3 milliseconds? Kinetics will help us to understand that part. So kinetics and thermodynamics really are useful tools when it comes to science, and they're both complementary. You need one to answer if the reaction's going to go, and the other one will answer how long it will take to occur, which is also kind of cool. So let's look at a general reaction. Let's talk about little red atoms A turning to little blue atoms B. And you can see down there in those 3 little jars, which are taken at 20-second intervals, at first you have all red, 1 mole of red A and no blue B. Then after 20 seconds, you're down to a little bit more than half of a mole of red A, but now you've got almost half of a mole of blue B. And after another 20 seconds, or when 40 seconds has elapsed, now you're down to only 0.30 moles of A, and now you have 0.70 moles of B. So I want to make some things that are state some things which I hope are very clear. In a reaction, the reactants will constantly decrease, like you have less and less red the longer we wait, and the products will constantly appear. So we don't start with any blue B, we get more at 20 seconds, we have a lot more at 40 seconds. That's a general trend when it comes to reactants and products. Reactants disappear with time, all right? And when it comes to reactant rates, we're going to put a negative sign in front of them, all right? We're going to see that both reactants and products, we're going to talk about the change in reactants and products. And if you remember since Chem 221, anytime you have a change with a little delta sign, it's always final minus initial. And because reactants are less as time goes on, final minus initial is going to give us a negative sign. So one thing you can do right away, we'll see lots of rates in this chapter. Every time you see a negative rate, it'll be a reactant. A positive rate will be a product because products appear over time. The final time should have more product than the initial time. And that's kind of a cool thing to think about in the back of your mind. Here's an example of how you can write the rates for this reaction. Now, this is dinitrogen tetroxide going to 2 nitrogen dioxides. And the rates here can be written in 2 different ways. First of all, on the left-hand side, you see there's this weird negative, and then there's a delta N2O4 and a delta T on the side. That would be a reaction rate for a reactant, okay? And we know it's a reactant because it has a negative sign in front of it. If we didn't have that negative sign, the change in N2O4, final minus initial, that would be negative. So like you can imagine that this part right here, the delta N2O4, that would be a negative quantity. So we put a negative in front of reactants just to make the overall rate positive. I think people like having positive numbers, honestly, better than negative numbers. In the denominator, you have delta time. Temperature is usually capital T and time is usually small t. So again, like all deltas, it's final minus initial. So delta time would be the final time minus initial time. Cool. But what if it's easier to study the reaction rate for a product? All right, no problem. Well, in this case, you can probably imagine the part I'm kind of putting in big square brackets right here. You can probably imagine that the change of the NO2 product over delta T would be awesome. We'd put a positive sign in front of it to keep everything positive. But notice that 1/2 factor, okay? Because NO2 is appearing twice as fast as N2O4 is disappearing. And that comes from the 2 to 1. Like 2 NO2s are appearing for every 1 N2O4 that's disappearing. So another thing you have to do when it comes to reactant rates in kinetics is you have to go 1 over the stoichiometry. Now notice for N2O4, there was no 1 over 1 because that's just 1, all right? But if you have a different stoichiometry, 2, 3, 4, whatever, then go 1 over that value. So there's a 1/2 over the delta NO2 over delta time. If you do these two things, if you put a negative sign in front of the reactant rate and you go 1 over the stoichiometry, then chemists, scientists, and you too can describe the rate of the reaction from either a reactant or a product's perspective. All right, it doesn't matter. And this is really cool because your lab maybe has the technology to study the N2O4 decreasing over time. So that would be like finding a rate of a reactant. And maybe my lab has a technology to study the NO2 appearing over delta time. That would be the rate of the product. We can compare our answers if, again, you put a negative in front of the reactants and you go 1 over stoichiometry. This is kind of a cool thing, but it's a lot different than in our real world. Like, here's an example. Let's say I said, hey, how fast did you drive up to Hood River yesterday? And assuming you did go up to Hood River, okay. Well, you'd probably say it was so many miles per hour. That would be the change of miles. So you started at 0 and went to about 60, we'll say. So 60 over maybe an hour. So 1 hour minus 0. That would be like your speed, okay. But in chemistry, you can talk about the speed from both directions. You can think about it as arriving at Hood River from Gresham, or you can talk about it as going from Gresham to Hood River. And in chemistry, you can do this for reactants or products, again, as long as A, you put a negative in front of the reactants to make all the numbers positive, and B, you go 1 over the stoichiometry. Here's another example of what we just talked about. In this reaction, N2 and O2 are combining to make NO. So notice 2 things. First of all, we have 2 reactants, N2 and O2, and we have 1 product, NO. And NO, the product, has a 2 factor in front of it. So what you can do is for the reactants, you can definitely, and there's just a stoichiometry of 1, you can just say, hey, no problem, rate equals negative, because it's a reactant, reactant, delta, final minus initial, N2, over the change in time. And on the right-hand side, you can see what that means. It would be the N2 final minus N2 initial, T final minus T initial, et cetera, et cetera. You can do the same thing for the O2. All right, it's another reactant, so it would be delta O2 over delta time, and you can see that. However, if you wanted to relate this to the NO over delta time, you can do so. 1 over the stoichiometry would be 1/2 delta NO over delta T. And notice we didn't put a negative in front because NO is a product. So the reaction rate for this reaction, we can talk about it as the N2 disappearing, we can talk about it as the O2 disappearing, or you can talk about it as the NO appearing. And all of those ways are ways that we can get the speed of the reaction, which is a pretty powerful thing, because often, again, it'll be easier to study the reactant disappearing or the product appearing, and it doesn't matter. As long as you translate the numbers by putting negatives in front of reactants and 1 over the stoichiometries, you're good to go. Here's another example of how this process works. This is a reaction where you've got some blue dye, and if you add bleach to it, it will actually take the color of the blue dye out, so it gets like clear. And there's a graph down there, and dye, we're assuming, is just a single stoichiometry of 1. It's a reactant, so we're going to have negative delta dye over delta time. All right, and again, it's a reactant, so it's negative. We're going to assume it's the only thing, so it's a stoichiometry of 1. Now, instead of having final minus initial, you can see there's some actual numbers in there, and we'll talk about this. This comes from the graph. So at the end, the final dye concentration, 2.00 times 10 to the minus 6, while the initial concentration was 3.4 times 10 to the minus 6. So you can see just the part in parentheses right there. Initially, that would be a negative number, but there's a negative in front because dye is a reactant, so it'll end up being positive. And this is the change over 1 minute. So delta time would be 1 minus 0, or 1 minute. So this is a way to actually calculate the rate. And that 1.40 times 10 to the minus 6 it's molarity per minute, basically. That's like a speed, all right? That is a speed in chemistry. So unlike a car, which goes miles per hour or kilometers per hour, if you're in a cool metric country, all right, these kind of speeds are usually going to be things like molarity per minute, which is what that is. Sometimes you'll have moles per minute. There's different things like that, but it's always some kind of chemical quantity per unit time. And in this problem, because these are all concentrations in moles per liter, the speed will be molarity per minute. All right. Molarity, remember, is moles per liter. So in the little blue text there, they just rewrote molarity as moles per liter per minute. The liters and minutes are both in the denominator. Blue dye oxidized with bleach. Concentration of the blue dye is going down. Each of those red dots on the graph is a value of the dye over time, and you can see they're constantly getting smaller.
Pouring bleach into a beaker of water and blue food dye converts the dye molecules into a colorless form. The timer indicates the progression of the reaction. If we plot the concentration of dye molecules at various times over the course of the reaction, we can determine the rate of the reaction.
So in this problem, they had a timer, and then every minute they essentially took a sample out, analyzed it. They did this for a couple of minutes to get those values right there. You can actually then find the rate, like how fast things go, by a plot like this, and it's pretty cool. A couple of things about the plot. So remember, this is a reactant, and reactant concentrations are decreasing, like we talked about. But notice how it doesn't just automatically go down to 0, and that's going to be something else we'll talk about later coming up. There are lots of different rates that are possible in kinetics, all right? And I just want to show this graph as a list of some of the possibilities you can get. Now, what we're going to do most of the time in Chemistry 222 and Chem 223 is what's called an average rate. All right. And it's the average rate. You look at some small value. You take the change in the reactant concentration over the change in time, and you're good to go. All right. And that's what the top one is right there. So we're going to look at speeds that are like 0.0080 molarity per minute, stuff like that. However, you can also have what's called an instantaneous rate. This is closer now along with calculus. If this sounds familiar, you should. An instantaneous rate would be like the rate of that one point right there. And in an instantaneous rate, you can actually find that the speed of the reaction is decreasing and stuff, which is totally fine. And you can also have then just an overall rate of reaction, which is usually over a longer time. All right. All of these are valid, and there's uses for all these types of rates. We're usually just going to look at the average rate. However, kinetics and calculus do go well together, but you don't have to have any calculus for this class, so don't worry. It's okay, man. But anyway, in calculus, you'll learn some more techniques, and in a third-year chemistry course called physical chemistry, you might look at these other kind of rates in more details, and there's lots of neat things you can do with them, but it's more than we need for Chem 222. So just realize most of the time we're just going to look at kind of an average rate over a specific time. So here's a kind of question you might see. It says, what is the average rate of this reaction over the first 2 minutes? Okay, and there's all these different numbers there. So the time axis is usually the x-axis, and what it's saying is it wants to know what is the rate between these points, like where the reaction starts at t equals 0 and where it ends at t equals 2, which where it ends for this problem, all right? And what you want to do is you're going to have a delta reactant concentration over delta time. You want to make sure you put a negative in front of these values, otherwise you'll end up with a negative value. So on the top part, all right, final minus initial, and final is the time at 2 minutes, and that's going to be this value right here. So if you go over here, I don't know, maybe this is 1.7, 1.75, something like that. And from 1.7, we would subtract the value up there. So I don't know, that looks like it's not quite 3.5, maybe 3.4. So tentatively, I would say, okay, this must be then 1.70 minus 3.40. That's the change in the concentration. It doesn't say what chemical it is, doesn't really matter. That's the 1.7 minus 3.0. And again, I just read the values from the graph, and I may not have read them very well. These are always susceptible to the doubtful digit, all that kind of stuff. The bottom part, final time minus initial time, well, the first 2 minutes, the final time would be 2 minutes, and there we go. And the initial time would be 0. And that would be the delta T part of the rate. Now, initially 1.7 minus 3.0 would give us a negative number. So because this is a reactant, I need to put a negative sign in front of it. So if you do all of this, and again, we'll see what kind of answers I did actually in this calculation. I came out to be 0.85 moles per liter per minute. So you can see how 1.7 minus 3.4 is actually initially negative 1.7, but we make it positive because it's a reactant rate, and reactants get a negative sign to make them positive. And then in the denominator, it was 2 minus 0. So 1.7 divided by 2 is where the 0.85 number came from. And this 0.85 moles per liter per minute, or 0.85 molar per minute, that's the speed of this reaction. And that's pretty cool. Now, technically, it's just the speed of the first 2 minutes, et cetera, et cetera. There's lots of other types of ways to analyze speed, but this is how you would calculate it, all right? You would have these values, these concentrations or amount values over different times, do the difference between the concentrations in the numerator, difference in time in the denominator, calculate it, good to go. There's lots of factors that affect how fast a reaction goes, or lots of factors that affect the rate. And those include concentration. So the more reactant you have, sometimes that'll make a big difference in how fast things go. The temperature absolutely makes a big difference. Hotter temperatures usually make reactions go faster. The surface area can be a big deal. If the substance is very dense, a lot of times the reaction will only happen on the surface of the substance. So if you have a lot of surface area, you will have more reactions. And finally, a catalyst is something that speeds up a reaction, but it doesn't actually participate in the chemistry. It's actually regenerated at the end of the reaction. Catalysts will make reactions go faster. Catalysts are pretty cool. We'll talk about all of these as we go through this section.
In the test tubes is hydrochloric acid. On the left is a 0.3 molar solution, and on the right is a 6 molar solution. If we place a strip of magnesium metal in the 0.3 molar solution, the metal begins to react slowly. If we place a similar magnesium strip in the 6 molar solution, the reaction is much more vigorous. Within moments, the reaction is complete. Meanwhile, most of the magnesium in the 0.3 molar solution is still in solid form.
You can see here that the 6 molar HCl doesn't mess around, man. It reacts super fast with that magnesium. And assuming the two pieces of magnesium were the same mass, and it looked like they were, then, oh wow, yeah, 6 molar HCl reacts a lot faster than the 0.3 molar HCl. So this is just an example as telling you that the concentration does make a big difference. I've seen this in the lab. For a while, I tried to use like 0.1 molar HCl with some zinc, and it worked okay. But then I thought, I'll put in some 6 molar, and man, that thing shot off and stuff splattered around, and I was glad I had my safety goggles on. But anyway, needless to say, yeah, rates can be definitely influenced by the concentration. So 0.3 went relatively slow and 6 molar went super fast. Now those graphs on the right-hand side would show graphically what this means. You can see the 0.3 molar graph, it's definitely like stretched out better. Like you can see there's a value all the way down to 400 seconds. On the other hand, the 6 molar HCl on the same axis, wow, it was done in like 10, 15 seconds. So you can see it's very, very steep. So the molarity of the HCl does make a big difference how fast this reaction goes.
On the plate is a pile of lycopodium powder. If we aim a flame at it, not much happens. If, however, we take some of the lycopodium and then spray it into a flame, the combustion reaction is explosive. The more surface area of the lycopodium particles that is exposed to oxygen, the faster the reaction.
Lycopodium powder comes from a type of a mushroom, apparently, and it's very dense, very thick, all right? And when you try to put the flame on it directly, not a lot happens because it's so thick, you just have reactions happening on the surface of the lycopodium powder. So, but the difference here is that if you spray it through the flame, oh man, now you've got individual little particles of lycopodium. They all react very quickly in what's essentially a combustion reaction to make some pretty cool things. Sometimes magicians will use lycopodium powder to make like little flashbang kind of things in their demonstrations. It can be pretty cool if you know, of course, what you're doing. But this is more importantly here, it shows how the surface area can make a big difference. Sometimes if you try to react a raw piece of metal, it's very slow because the metal also, like the lycopodium powder, is very thick. But if you can get the little metal into little tiny pieces or fragments or splinters, then it usually reacts a lot more quickly.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
This is a video I showed back in Chem 221 when we were talking about stoichiometry. And I just kind of talked very fast about a catalyst. But a catalyst can be super useful for humans in many, many ways. This is an example of hydrogen peroxide, H2O2. And hydrogen peroxide, if you buy it at the store, is always sold to you usually in a brown bottle. And it says keep in the refrigerator. Okay. The brown bottle is to keep the air, the sunlight out, because it will make it decompose, and the cold of the refrigerator just makes it react slowly. However, if you want the reaction to go fast, you can add a little MnO2, manganese 4 oxide. Thank you, not manganese dioxide, if you remember the nomenclature lab. But anyway, the manganese 4 dioxide acts as a catalyst, so it makes the transformation of H2O2 into water and oxygen occur much more rapidly. The neat thing about a catalyst is that at the end, where you'd have just oxygen gas and probably water left in the flask, you could evaporate off the water or filter it, whatever, and reuse the MnO2. Catalysts do not participate in an absolute sense in the chemistry. They'll make something happen, but they will be regenerated at the end. So you could have the MnO2 go through many more transformations. If you took Chem 221 at Mount Hood Community College, or even Chem 151 sometimes, there's a percent potassium chlorate lab. And in that lab, we also used MnO2 to make the decomposition of the KClO3 occur a little bit faster. MnO2 is a relatively inexpensive catalyst, which is nice, so we can use it. If it was expensive, we would absolutely be recovering it, recycling it, reusing it again, stuff like that. So to summarize, a catalyst just makes a reaction go faster, but it's not used up in the reaction. So you can reuse the catalyst sometimes over and over and over for many tens of thousands of transitions.
If we pour equal amounts of hot and room temperature bleach into separate beakers of colored water, we see that the hot bleach on the left destroys dye molecules more rapidly than the room temperature bleach on the right.
Temperature definitely affects how fast a reaction will go. Warm temperatures tend to make reactions go faster. Cold temperatures tend to make reactions go slower. And I feel this way myself when I go out on a cold day. I'm just not quite as enthused, ready to rock and roll. On the other hand, on a nice warm day, I'm like, yes, the sun is out. I'm feeling good. I'm feeling more excited. I think I react faster. So, chemical reactions are like your weird instructor, basically, but hopefully you get the idea. We'll talk about why temperature makes such a big difference in this chapter.